This is the lecture number 2 for our risk management series, and I'm going to minimize that. In lecture number 1, it may not have all hung together so well because I was trying to give you just a general background on risk. And what we're going to talk about in lecture number 2 here is, okay, so we've talked about risk in general. How did and how does NASA do it? And what lessons are relevant for us from that, both good and bad. So I spent a fair amount of time in the first lecture talking about the difference between vehicle-centric and person-centric risks. And we're going to get into that a little bit more during this one. And part of the reason why is because that difference between vehicle-centric and engineering-centric has generally caused consternation, let's say, at NASA internally. And the reason why it does is because the vast bulk of risk assessment that was developed at NASA was focused on vehicle-centric risk, right? What happens if something on the vehicle fails? What happens if the vehicle blows up or something doesn't work, right? And vehicle-centric risk is important, but it's also different from human or person-centric risk. And that's a little bit why I kind of gave some of that background on why it's important to look at both. So if you think about the history of NASA, when we started early 1960s, flying people in space, and Roscosmos had these same challenges, or the Soviets at that time had the same challenges, right? You can do a bunch of analyses for risk on a vehicle that you've designed, but you didn't design the human. You're learning about what their risk modes are in a new environment throughout the history of human spaceflight. And so this area causes a lot of tension because for the most part, early humans tolerated things reasonably well, and they became sort of a dumping ground for risk. You need your things to operate at a higher temperature. Okay, the crew can take a little bit more heat. You need more space for the fuel tanks. Okay, well, you can encroach a little bit on the private sleeping quarters, or maybe we get rid of them entirely, right? And in early space flight, when we're talking about things that are, most of the space shuttle missions, for example, which were 2 weeks or less, the human contribution to risk was much smaller than the vehicle contribution to risk. And that sort of becomes a different ratio when we go farther and longer. So you got to be aware of this tension, right, between these two different ways of thinking about risk, because your engineers will always think about it from the vehicle perspective, and we are still trying to get the field to understand the person-centric side of this. So let's give a little bit of history, right? I mentioned that in early space flight, it was one thing, it was all engineering risk. The engineering challenges of getting into space were a bigger problem than the human survivability if the vehicle worked, right? And so eventually, as we started politically looking at more long-duration space flight beyond Skylab, and remember, the Russians had been doing a bunch of space station work, and they were far ahead of us, actually, in this capability. On the NASA side of the coin, we had to ask these questions of, well, how do we learn more about how the human's going to do with longer time in space? Because we were kind of spoiled. The longest Skylab mission was 84 days. The Russians were flying people for longer. They weren't necessarily sharing their data with us. In 1997, the life sciences directorate over at Johnson started a Bioastronautics Roadmap. In 98, they created or included the National Space Biomedical Research Institute, NSBRI, which eventually morphed into TRISH, the Translational Research Institute for Space Health, that exists today. In 2000, they said, hey, we need to think about all the risks on the human side, and they pulled together 55 risks and 250 questions and started to configuration control what we were thinking about risk on the human side. And this was kind of the beginning of that process, right? So they were trying to get their heads around it, and they clearly pulled on some, what have we learned so far at spaceflight? But it wasn't It wasn't something that was configuration controlled before this point. Why does configuration control matter? Because it keeps an ongoing record of what you have learned and what you have decided based on the things that we have learned. And before that, we weren't doing that, at least not on the human side. So in 2001, and if there's anything that I suggest that you read out of this whole thing, it's actually this: Safe Passage, Astronaut Care for Exploration Missions. NASA went to the Institute of Medicine, which is now the National Academies of Medicine, and they asked for some help with thinking about how should we approach this problem of human risk in spaceflight. And the Safe Passage book was their response. And what's fascinating about it is it was published in 2001, and here we are in 2026, and you can see how we've done. In some areas, we haven't done almost anything. In some areas, we've actually made a lot of headway. And so as a result of these recommendations, the NASA then identified a strategy to name the human as a critical subsystem of spaceflight. And here's the engineering terms, right? Tolerance limits and safe operating bands should be established. And then in 2005, that Institute of Medicine reviewed, hey, what is NASA doing along these lines to respond to that thing that we wrote them in 2001? And this was NASA's work, a risk reduction strategy, and it was the start of the Human Research Program, right? That is when it was established in 2005. So I'm just giving you this history because, like, you can hear about these things, but nobody ever explained to me where the hell they came from, and I had to go piece together the history of these things, right? So going from a very vague and nebulous approach to risk to something that started to be more rigorous, and also had an associated research program whose job was to go and figure out what are the human risks of spaceflight and how do we mitigate them? How do we bring them down to something smaller and manageable so we can go farther and do better, right? Now, here's another term that you might have heard of that you might not know what it is. In 2006, there was a Health and Medical Technical Authority established, right? The HMTA. Eric, what the hell is a technical authority? After the Columbia broke up, the Columbia Accident Investigation Board said, hey, people in NASA, the management has been too susceptible to the pressures of schedule and budget, and we need somebody who is separated from that, who can throw a flag on the field and say, wait a second, we need to slow down here and do something differently, right? That was the challenge with both Challenger and Columbia, right? In Columbia, they didn't believe that the ice that hit the leading edge of the wing was something that could actually cause the type of damage it did. And so after Columbia, they established these technical authorities. The CABE actually recommended an engineering technical authority. NASA established 3 of them: the engineering TA, the safety admission assurance TA, which is where most of the risk work for NASA was being done in general, and then a health and medical technical authority. And in that role, all of a sudden now you have somebody who's responsible for saying, hey, here's what we think our standards are for human spaceflight. Now, before 3001, we actually had 3000, right? It became something that was a part of the Health and Medical Technical Authority responsibilities, these standards. And the first one, that is at 3001, Volume 1, talked about, hey, here's what we know we need to do, at least, to protect cardiovascular, musculoskeletal, a number of other areas for humans. And that feedback loop that gets created there is something that then has to be fed and monitored. And so they created a human system risk board, which was underneath the Health and Medical Technical Authority, whose job it is to specifically look at these things. And they were like, how can we do this in a rigorous way? And they created a tool called the Risk Management Analysis Tool, RMAT. That morphed into what I'm going to show you today over time. Okay. 2011, they realized that it's about more than just the human. It's about how the human and vehicle put together. And they actually make the volume 2 of 3001, which is Human Factors, Habitability, and Health. That's the one that has things like your touch temperatures on the dashboard should not be higher than this much, right? And things like that. No sharp edges, okay? And in 2014, they go back to the national academies, which used to be the IOM, and they say, hey, we're really struggling when we look at these long missions with how we should ethically do this, right? And so there's actually a report called Health Standards for Long Duration Spaceflight, where the national academies made recommendations on the ethics of how you do the risk management, especially in domains where, like looking ahead to Mars missions, we don't know what the hell is going to happen because we just don't have any data out there, right? Everything is kind of speculatory and guesswork. And then in 2018, as you notice here, Antonsen chairs the HSRB. That's when I came onto the scene and started learning about all this stuff and trying to figure out how do we make it better, right? So what you're going to get today is what does NASA do now? A little bit of what they've done and trying to paint that picture of how do we then deal with risk from the NASA perspective, which has its strengths and its weaknesses. And you got to be aware of those because it's not the only way to do this. So safe passage I mentioned, right? This is an important one. This one is highly recommend you go read. It's not very long. It's a tiny little book. Their charge to the committee was to develop a vision of space medicine for a long duration space flight. This is actually part of the reason why we have separated out and started creating space medicine fellowships that are different from the preventive medicine fellowships of the past. Is a big part of what this book actually laid out over 20 years ago. Okay. And there's a couple of themes there that persist, right? We don't yet know enough about all of the risks to human health. And we should be doing everything reasonable that we can to gain necessary information before humans are sent on those missions. That's literally why the Human Research Program was created, was to go and try to figure this stuff out. Okay. The second book that I mentioned part of the way through that history is this Health Standards for Long Duration and Exploration Spaceflight. So you will hear lots of people talk about, we haven't done enough on ethics and human spaceflight, blah, 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 blah. We have done a ton of work on ethics in human spaceflight. As a matter of fact, the national academies have weighed in on that work. And this is sort of the culmination of a lot of that work as of 2014 that still applies today. You can have some problems with it, and I do, because I've actually written some papers that got smashed inside of NASA that they kept us from publishing because they didn't want us to disagree and make it seem like NASA didn't know what they were talking about. I'll be publishing it later this year. But the work has been done, and usually it comes down to a value decision. So knowing what was said in this work is really important to making sure you understand and are speaking from a place of knowledge about ethics in long-duration spaceflight. All right. So now I'm going to change gears, right? I told you that the engineers handled risk differently than the human side of the equation. And we're going to talk a little bit about how did the engineer think about the human? And if you remember back, if you've ever watched The Right Stuff, you'll see these scenes where the Mercury astronauts are kind of at odds with some of the scientists at the engineers on Werner von Braun's team at the Mercury program about, should we put in a window? Should we put in exploding bolts on the doors and all these sort of things? And you get the sense that Werner von Braun's team was like, you guys, we don't want you to do anything or touch anything. We just want you to be along for the ride like a monkey. And the pilots, as you can imagine, didn't take that very well. And they said, hey, the only reason you guys are getting funded is because people are going up there. And so if we decide to call bullshit on this and call your bluff, no bucks, no Buck Rogers, right? You guys will lose your funding. And that tension has existed in some way in NASA ever since. So let's think about how the engineering considers the human. Okay. What I'm showing you here is a risk analysis that looked at the decision that was going to be made at that time. This is 2006, about whether or not we should go and fly a Hubble Space Telescope repair mission, right? And what you see here is STS-115. How much risk do we have? 2008 predicted ISS mission. How much risk do we think we have, right? And by risk, our outcome is loss of crew. You see this over here? How likely are we to lose the crew? which basically translates to losing the orbiter, right? And then if we said, hey, well, and notice the date, right? This is after Columbia. So they're worried about what happens if ascent debris damages the wing again. Should we have no rescue crew set up, or should we have a rescue crew set up? What does the risk picture look like? How does it change based on having that redundancy there, right? So why am I showing you this? I'm showing you this because it shows you the way that different risk things were stacking for the engineering, right? MMOD, micrometeoroid and orbital debris, a 1 in 281 chance that it would do damage to take out or cause a loss of the orbiter of the vehicle. Ascent debris, this was for STS-115, which was before, 1 in 421 chance that ascent debris would take out the orbiter. Space shuttle main engine failures, right? This is what killed the Challenger, 1 in 667. And you see these other entry problems, other orbits, right? These are all ways that we calculated risk about the hardware and other things like orbital debris, for example, and how likely they were to fail. And what you see here is that when we look at some of these things with and without a backup rescue crew, right? Ascent debris might not kill it on the way up. It might kill it on the way down, right? Other ascent things. And so what you're saying is if we actually had a backup crew, we would take a 1 in 65 chance of losing the crew and drop it down to a 1 in 76 chance of losing the crew. And what you then have is now an entire orbiter sitting on the pad, ready to go with a whole crew and all the costs associated with it, right? So the risk and the cost are two things that you now have in your pocket. How much safer are we? And is that worth it, right? So this is how risk is thought about or was thought about at that time. And where do you see the human in here, right? Nowhere. Okay, this is risk that is flooded with all of the potential failure modes of the vehicle, right? And remember I said there always has to be a belly button, somebody who decides where the threshold is, right? For something this big, it's the NASA administrator, okay? That is the person who has to make this decision. So this shows you how risk stacks up from different sources and how they were thinking about it. Now, you didn't see the human in part because, for one thing, it was actually considered a much smaller area. What we have here is human error falling somewhere between space shuttle main engine and ascent debris at 1 in 770 cases. Okay. These are scenarios that involve human error and provide a significant risk contribution, right? This is the Homer Simpson, what does this red button do type of thing. And he stupidly pushes it and everything blows up. So what are the odds that something like that happens? In human error, most of the time it's talking about piloting, okay? Landing the space shuttle, for example, which is a big one. But there are other things that human error could contribute to. So here you can see mechanical failure and human error that result in failure to lower the landing gear, right? That's how they were thinking about it. Did the human mess up lowering the landing gear or not? Okay. So this is where human error starts to enter the picture. And so what they would look at is, okay, what are the conditions that might cause them to fail to do this critical task, right? Degraded or extreme environment conditions, unfamiliar tasks. There's a lot of stress if the task is too complex, right? So what you're seeing here is crew error during entry is contributing some probability, right? Things that are non-crew, collision of the orbiter with the, these are the top contributors involving human error. What if they drove the orbiter into the space station during rendezvous and docking? Sounds stupid, but it happened on Mir with the Progress vehicle, right? They were piloting it remotely and drove it into the space station and nearly killed everybody, right? So it's a very real risk. What if they inspect and they didn't catch any damage that was done on ascent? And you can go down this list of things, right? And it's the ways that humans didn't catch or fix problems that happened on the space shuttle, right? So it's reasonable to ask yourself, right? Is this a human error because they didn't actually make up for the design problems? Or is this a vehicle error that then overwhelmed the human self-repair capabilities for the system? But this just gives you insight into how they think about it, right? Um, and this is what we at NASA dealt with for a long time up until we started those processes of creating the how do we think about human risk. So reliability analysis became a thing, right? Human error for the space shuttle. And here's a quote on some of these things from Hamlin's article. Special attention should be paid to critical crew and human actions required for a nominal flight, and that these contributed to around 10% of the overall shuttle risk, with the other 2% human error contributing relating to responses to failures, right? Something in the machine failed and the human didn't fix it. So now keep in mind what we're saying, right? We're starting to talk about cognitive things. Can the human observe? Can they interpret? Can they plan appropriately? And can they execute a fix? Okay. Cognitive error modes, but they're still being seen as the human as a cog in the system that has some probability of failing, right? So all of these things assume that the human is in good health, that human error was solely a cognitive issue for whatever reason, right? Well, what leads to cognitive problems? A lot of them have to do with other things besides just, are you in good health that day? A lot of them are health related, right? Cognitive function is a type of performance. So what if the crew couldn't physically accomplish the task because they were sick or injured? What if they couldn't accomplish the task because of the way the system is designed? Those are both failure modes that are sort of deeper in than they were going with human reliability analysis. What if they weren't trained adequately, right? These are all things that contribute to these cognitive error modes, but aren't being flushed out here. And the challenges as we think about going longer into space and with all the things that crew have to deal with in space is that we recognize that the contributions to cognitive function and human error are actually a multifactorial thing that's going on with the whole system. And so we had to rethink how we're doing risk. So here's a way to think about it, right? Because remember, all of that stuff is focusing on the human as something that is failing in many cases by not fixing something that broke on the vehicle. All right. So let's talk about pilots, right? National Transportation Safety Board analyses of just aviation, right? Aviation is a well-characterized thing. In the looking at pilot mitigation of safety and operational risks, one of the things that we see about major aircraft malfunctions, right, is that you have all these accidents, major incidents, right, different events. What you're not seeing oftentimes is line operations safety audits, okay? These are things that were like caught in line operations and didn't turn into an accident because honestly, in reality, it's because the pilots were there to catch them and fix them, right? The pilots were functioning well. And they're a threat in 20% of normal flights, according to NTSB data, right? So what are the humans bringing, right? They're bringing adaptable and creative resiliency to a system that is designed in a certain way. And one of the major findings by the National Transportation Safety Board is that pilots successfully manage equipment malfunctions as threats that occur in normal operations, right? Over 40% of failure modes were not anticipated by the designers of vehicles. And in these cases, the pilots have to rely on their own knowledge, skill, and airmanship to mitigate risk because there was no procedure to follow. And this is in an industry that is vastly more mature than where we are in human spaceflight. Okay. So what I want you to take away from this, and now this is me speaking as a PhD level aerospace engineer, is that when an engineer tells you not to worry about it, do not trust them. Okay. There is always large rooms of domain where the designers have not been able to anticipate the behavior of complex systems. And that's why we talk about risk in a lot of different ways. Okay. So that's how engineers thought about it, right? Cognitively, can the humans fix the problems that we designed poorly into the system, right? So if this cognitive error is such a big deal in a 2-week space shuttle mission, right, 1 in 770 failure mode, right, how big of a deal is it going to be in months or years-long exploration missions, especially when you start taking away the advantages that we had in low Earth orbit, right? And you see them here. Real-time communications, the evacuation capability, the strong consumables resupply. When we go back to the moon, yeah, the communications are still going to be near real time. But now your evacuation capability stretches out to 3 to 11 days, potentially, at least for the Artemis program designs. You have limited consumables resupply. You can't just send something up. There's a much longer supply chain. So if you run out of things, it's a bigger deal than it was on the space station. And when you start going to Mars, right, you lose all of those things. You don't have any real-time communications. You're looking at a 3-minute one-way signal from Mars to Earth at its closest approach at the speed of light. And at its farthest, it's about 22, 23 minutes one way. So now you're talking about potentially 45 minutes before somebody responds to you when you send a question to them. And that's a big deal because we've never operated in that domain. And then also take away that we don't have an evacuation capability, that we don't have consumables resupply, right? And this increasing exposure to hazards means that that crew is now getting deconditioned over the entire duration of that mission. So now we need to ask the question, how good is their cognitive function going to be in this arena where all of a sudden we're asking them to do so much more with so little? So that brings us to prevention and risk characterization, right? This is one side of the coin of risk. And we're going to start mapping out what NASA has done about this. So not just NASA, right? If we can never talk about risk without acknowledging something that you'll hear from the aviation community. It's called the 1%. This comes from aviation. It was derived in the 80s, and it applies to two-pilot commercial transportation. And they look at the most risky part of airline operations, which is the first 3 minutes during takeoff and the last 3 minutes during landing, as critical time periods. And the 1% rule assumes a target all-cause fatality accident rate for commercial, like big public transport, of one failure, all-cause fatal accident rate in 10 to the 7th flying hours. And then you see these other things. Not more than 10% of which should be due to one system failure, for example, pilot failure. Now, that's why you have two pilots, right? And not more than 10% of systems should be due to a subsystem failure. For example, in the human side, medical incapacitation, right? So the target fatal accident rate due to aircrew medical incapacitation is one accident per 10 to the 9th flying hours. One accident in a billion flying hours, okay? That's where aviation safety is targeting. And remember, we're looking at one accident in 90 for the space shuttle, right? The difference between these couldn't be any bigger, but it's instructive to understand this 1% rule because it talks about how do we think about humans and risk, right? And so you can see the Mitchell's and Evans paper down at the bottom of this that you can go read, right? But when they formulated this 1% rule, in-flight capacitation was sort of considered to result in a fatal accident about 1 in 1,000 events. And so in order to avoid that, neither pilot should have a risk of medical incapacitation greater than 1 in 106 hours, approximately 1% in a year of 8,760 hours. Now, what does that all mean? You should not have a pilot have a likelihood of not being able to fly the plane due to incapacitation. What are the reasons for incapacitation? It's not always heart attack or stroke. The number one reason for incapacitation in airline pilots is actually diarrhea and abdominal problems. And it's not immediate incapacitation, which is why two pilots can make sense in this domain. Okay? But we're not here to talk about aviation. We're using that as a reference point for, well, wait a second. How do we talk about it in the context of astronauts? Because just like most of the passengers on a plane are not a pilot, right? Most of the astronauts who are flying these days are not piloting a vehicle. Even on Inspiration 4, when the woman went up and she was piloting the vehicle, right? She was pushing in some buttons and the vehicle was mostly running in an automated fashion. Okay. So it's just something to keep in mind is that do we really worry as much about incapacitation when people aren't like sitting there with a stick during launch and landing and takeoff like an airplane? You have to think of it in a different way. And so this is how different groups have thought about it. They've started to stratify the different consequences of events, right? What are the classes of in-flight medical events? And you can see these are pretty minor: event severity, performance degradation, mission impact, resource utilization, right? These are a little bit bigger. These are a little bit bigger. And then class 4 is like, oh, this is the worst, right? So we're starting to grade these things in terms of clinical risk between 1 to 4. Okay. And then they start applying it. So the MSMB is the Multi-Systems Medical Board for the ISS. It's a multilateral board that makes decisions about medical things for the crews and how we're going to do them and what decisions are going to be agreed upon between all those different international partners, right? And so what they did was they met a medical disposition category, right? Disposition 1, disposition 2, disposition 3. You're going to evaluate these folks, and if they get to the highest level of capability, then they can be eligible for a 180-day mission. And that was extended to 220 days on a specific basis. If they don't, that's long duration space flight. If they don't meet that, then maybe they'll only get 30 days of space flights, short duration. And in some cases, depending on their medical things, maybe they can only do training. And this is very real. Folks who have had issues with SANS in the astronaut corps have in some cases been remanded to training only, or in some cases limited to only short duration missions. So this is actually used, right? And this is a preventive thing. This is saying we're going to look at you and we're going to try to keep you out of the action if there's a chance that you may end up, not either getting hurt more yourself or bringing risk to the mission. Brian, I see your hand up. What's up?
So sorry, quick question on that one. So is that analysis, this isn't done to decide who gets into the astronaut corps. This is like mission specific. So they're evaluating for like this specific mission.
Exactly.
Okay.
So you see this term here, Med Volume A, right? Mm-hmm. Within NASA, there are Med A's and Med V's. Med A's are what did we select into the corps, right? So they're saying, okay, all of that has been met. And then on top of that, they're medically eligible for hazardous training for all of this sort of stuff. So there's a next level of things, which are Med Bs, which are all the stuff that we need to do to monitor and everything like that. But this is on a mission-specific basis. So you can actually get sick with something, have it fixed, and then go back into the rotation and be able to fly. So Mike Barrett did that. He was nixed down to 30 days, and then eventually they cleared him for a long duration flight, and then he went up on his last mission, right? So this is just like the agreements of how the different countries agree on, hey, how are we going to treat all the astronauts the same? And they have to bring all of their medical stuff up to this board, and they all review it together, right? And they all have to say, yea, verily, we agree, your person is probably not going to be the problem child, okay? This is preventive risk management. This is decreasing the likelihood of an issue. Okay. So that's great. What happens when we go farther away? Well, those questions that drove the development of those standards and of the tools that we use eventually became something that created the foundation for the Human System Risk Board, right? And what we ended up with was a set of standards that had to be informed by what we were learning, research, right? We're learning certain things when we fly. Some of it's research, some of it's ops experience, some of it's knowledge that the astronauts gain, right? And that stuff needs to feed back into that system. And so the HSRB was formed in 2008, right, as a place to discuss those high priority risks thoroughly and exchange evidence-based information and data. And they thought, hey, we need to bring together all these different disciplines that contribute to this stuff so that they can make maybe more balanced decisions than any one group would make on their own. This is why the risk board was born, was because it isn't just about the doctors saying, let's give our blessing. It's also about the rest of the folks who design things and create things and contribute in other ways. And so that RMAT tool was one of the original things that was a tool for the risk board to use. See, you create a risk. In this case, this example is radiation carcinogenesis. You list what the relevant standard is. In this one case, it's risk of exposure-induced death less than 3% at a 95% confidence level with application of a LAR below this risk limit. I will give you an entire lecture on radiation and how this stuff is determined in a separate lectures, okay? And then how does it contribute to the outcome, right? Mission length, timing dependent. And you see here, they're looking at different architectures. Crew exploration vehicle, ISS, Moon, Mars, right? These are the things that would eventually become DRMs. And then these are the questions that were asked about the categories and ways that these things were affected by this. Okay, so every risk that was created had one of these sort of sheets as a way for us to roll up the information and present it to people. And what we're really trying to do is to do or develop continuous risk management, right? You bring in some evidence, you say, hey, we think there's a problem here. You plan for it. How are we going to either figure out what's going on or mitigate it? You get somebody to stamp the stamp of approval on it, and then you track it. This is what I mean when I say configuration management before. Somebody's responsible for tracking and saying, hey, we've learned some new things because we were following it. Let's stuff it back into the system and revisit it and say, what have we learned? And what should we do differently? And that is what continuous risk management is. So those RMATs were a way to try to formalize the evidence that the presentation of evidence that said, here's what we do with risk. Another way to think about it is you put somebody in this environment and we've got those hazards of spaceflight that we really can't affect, and they lead to certain risks. And those risks, in order to mitigate those, we put standards in place for everything. But those standards don't always apply. So for a given program, we take those standards and we extract the relevant things and we say, here's the requirements for the program in order to protect the human. And that's the process that we move down. Once you get those requirements created for a program, it goes into that program flow, and then that program flies, and those people fly. And if we're doing our job, we are monitoring and collecting information, whether it's through clinical care, for research, occupational surveillance, any of these things, right? And that information goes back in and tells us to update what do we know about our risks, okay? If we don't plan out, and I mean in a systems capacity, the ability to monitor, capture information, and feed it back into the system, then we do not have information to improve our standards and requirements. It's why risk management is so important. So here's the high-level takeaway I want from you on this, right? When we talk about risks, we're talking about things that we don't know or don't know well. When we're talking about standards, what we're saying is, we think we know these things well enough that if we limit this exposure to this much, it's probably not going to cause problems for people. Or we think that you need to have this piece of equipment there to make sure that these people are going to stay healthy. Or potentially even you need to design your seat this way, right? In order to keep people healthy if a crash happens. So those standards reflect what we think we know at a current time, and they are not gospel. They get updated, or they should be updated as we learn more. In some cases, the standards are pretty good by now. In other cases, they're garbage, but they're the best we can do. So every time that you negotiate with engineers, every time that somebody says it's okay to waive a standard or a requirement, right? You, because of the human is a complex system and the vehicle is a complex system, you start to introduce the potential for downstream effects that we can't predict very well, especially in the context of behavioral health, readiness, team interactions, all those things, right? Which is why, we have these standards on anthropology, anthropometry, net habitable volume. How much water does a crew member need per day? Guess what? How often do we meet that? Last time we ever met that was in the Skylab program. We have not met the recommended amounts of water per day since then. Food quality, monitoring and alarms, right? You get pushback on all these things from the engineers. So the question mark is, how much is it okay to give? And when do those little things become big things? And in order to have those discussions, then we have to figure out not only how we know things, but also how to communicate what that risk posture is. If we want to affect change, we have to show why it's important to do this. Okay. So I'm coming back to that thing that was RMAT that is now today's thing, which is the matrix for design reference missions. So you remember that in the RMAT, you had different sort of missions across the top. Well, here we've got those different missions here. Low Earth orbit, short or long, 30 days, less than 30 days, or 30 days to a year. We're not really looking beyond that. Lunar orbital, same thing. Go around the moon. Is there anything different between that and low Earth orbit? Well, the radiation environment is different. You're farther from Earth. The resupply chain is longer, right? So yeah, there's a few things that are different. What if you add in the surface? Same thing. What if you're looking at Mars? Mars planetary missions between 730 and 1224 days is what we were thinking about. And this preparatory category is, well, what if we were to do something in cislunar space, not as far, but simulate the Mars mission, right? Where you can have controlled, delayed communications. And what you're seeing here are the different things that bring risk to the mission, right? What type of mission and how long? What's the gravity environment, radiation environment? How is the vehicle and habitat designed at a high level? Distance from Earth. What's the evacuation time, communication? And again, EVA, right? How are you doing EVAs and how many? Because a lot of risk comes along with EVA that wouldn't be there if you weren't doing any. And so the risk matrix that eventually was created for this looked like this. It was a 3x4, 3 on the likelihood and 4 on consequence. And it was broken down into ops and long-term health. And this is part of where we sat until 2020 when I was the risk board chair and we modified it up to a 5x5. So this is what red, yellow, green used to mean. Okay. Your consequences in mission could be death or permanently disabling injury or severe reduction of performance, right? This is equivalent to loss of crew. But remember, just injury to one person is different from injury to the loss of the whole crew. And so we struggled with separating those things out. Okay. So we started asking, how do the programs do it, right? You've got ISS and they're kind of handling their engineering risk in a similar way. What did it look like? So this is what the ISS Boston matrix looked like. This is the way that we roll up likelihood and consequence. And you can see here that there's a couple of definitions of likelihood, right? These are qualitative definitions. Expected to happen in the life of the program, controls are missing or insufficient, likely to happen in the life of the program. These are, let's bring forward problems, specific problems with the ISS. How do we think about how important it is to deal with this problem as opposed to some other problem? Okay. And here's where you list your expected consequences, right? There it goes from minor up to loss of the entire mission. Also, it's not just about operational. It's about safety. It's about cost, how much money is involved, and it's about schedule. Did we mess up our entire schedule for like a mission, for example, or a program? So that is ISS specific from the engineering perspective. And what we wanted to do was make sure that we were doing something that was very specific to the human system and its contributions. So we went back to person-centric risk, remember, as opposed to vehicle-centric risk, right? So what if it isn't the vehicle that fails? What if it's the human? And how do we define it? And this is a different set of outcomes that they were not using. Loss of one crew life, consideration of evacuation, loss of mission objectives as a step on the road towards loss of mission, right? Long-term health consequences. This is something that the engineering groups did not have to think about. And that inability to recertify an astronaut for flight, which means that the agency now cannot send back a veteran astronaut. And that's a risk to the agency in addition to the astronauts. So these outcomes become things that we need to create a new matrix for to communicate it differently. And this is what that matrix looks like. So you have the same 5 by 5 over here. You have likelihood ratings, 1 to 5. You have consequences. And we're going to go through what each of these are. So the consequences for in mission, which is the one we tend to think about the most, are either drawn up in a health impact or a mission objectives impact. And mission objectives are the performance side, right? Could somebody function well enough to get the job done? As opposed to, did somebody get ill or injured? And what you're seeing here is it ranges from minor temporary discomfort and insignificant impact of performance and operations, all the way out to major. And what I've put here are these consequence levels, 3, 4, and 5, and in this case, 2, 3, 4, and 5, have impacts to things that relate to our major outcomes that we're worried about, right? Not just loss of mission, but loss of mission objectives and task performance. Not just loss of crew, but loss of crew life. And what happens if we get to a point where we think we need to evac, right? These are human-centric, person-centric consequences. We also have long-term health consequences that we define. Health and quality of life, which is the analog of performance after you're done as an astronaut, right? So chronic debilitating impact on quality of life or requiring continuous support for activities of daily living. Something messed you up so much that you cannot function on your own, right? And in the health outcomes, career-related premature death or permanent disability requiring institutionalization. If you're like one of those motorcycle people who like didn't wear a helmet, got a brain injury, and now you're on a vent farm, right? You'd fall into this category, okay? Can't do things on your own. Or maybe there's some short-term self-resolving stuff that happened as a result of spaceflight. Somewhere in between here, but we're giving you definitions that are for each of these levels. And then finally, for that flight recertification one, right? There's not a lot of risk involved if you are immediately able to recertify for flight. Sometimes it takes like 3 months and takes a little bit of physical therapy or something. Maybe it takes a year. Maybe it takes more than a year because you got pretty messed up, or you're unable to be recertified and your career ends prematurely. And all of these things have happened with astronauts. So this is recognizing that there's a different risk category that, oftentimes is not acknowledged. And if you don't acknowledge it, it becomes a hidden source of problems for you. All right. So the last time a HSRB published something was when I put it out in the literature in July of 2023 that showed what the roll-up was for all of their risks across all of the design reference missions. And I continue to push Mary and Dan to put out updates. But as you can imagine, everybody there is busy and don't always have the time to do it. So unfortunately, this is the last one that we have from 2 years ago. So it's reasonable to ask, right? What does red mean when we say red up here, right? We've put it in this corner of high likelihood, high consequence for all these things. And it's there in a bunch of different places. And for a program, if something is red, like the ISS, if you have something that's red, it's going to be, hey, this is a no-go until we fix that. One big difference. Now, that's vehicle-centric. Now, human-centric is different. The HSRB holds red as an indicator of relative risk, right? This is more risky than some other things. But it could be that it's accepted by the decision maker who set the threshold for risk. It could be that something that's red at the HSRB is okay to go fly with, because we're going to say, you know what, we recognize that that's a risk we're taking and we're going to take that risk. And the belly button who can say that is the chief medical officer, OCHMO, or his delegate, the HMTA. So that's J.D. Polk at NASA or Terry Taddeo at Johnson Space Center, who's the HMTA delegate. So you can imagine that this has caused us some difficulty. If the vehicle people are thinking about it one way, red means nuh-uh, and the human people are thinking about another way, which means, well, realistically, we could potentially do this with this red. So that's a big challenge and an area where we're still trying to figure out how to align those differences. All right. But they've been working on trying to de-emphasize the color ranking, but it's also a very easy way for people to kind of get a sense of the field. All right. So I am showing you a goddamn nightmare here. Who the hell wants to read all this? Somewhere back in the past, before I got to NASA, folks decided they were going to configuration manage big and important things on PowerPoint slides, and it leads to a nightmare. These things should be configuration managed in reports, but I wasn't powerful enough to change that. So then what happens is somebody flashes this thing up on the screen at the HSRB, and everybody says, okay, and they hum and a haw, and then they all agree to do something, right? This is what it looks like when they roll up the information and try to get it to the highest level. The scientists who are doing this stuff do an awful job. They struggle mightily with trying to, condense down the information. And so what you're seeing here is risk statement, primary hazard, secondary hazard. What are the countermeasures? And I forced them to do monitoring because they only had prevention and intervention before. So they have monitoring, prevention, and intervention. Contributing factors, state of knowledge. Give us a little synopsis, right? What are the likelihood and consequence drivers for these different DRMs that are not green? And what's the disposition rationale? Disposition means, what are we going to do about it, right? Well, in this case, what you see is this little thing over here. You see the mission types, remember all that sort of stuff. And then you'll see, hey, here's where we think our risk is for this in terms of, this is the cardiovascular adaptations risk, right? Low Earth orbit, we've accepted it. If it's long, we put in monitoring, right? Then there's this other term, optimization, which is very hand wavy. And then down here, you see some of these things requires mitigation and standards refinement for long-term health, or requires mitigation and standards refinement for ops type health things, right? So this is how they roll it up and show the picture across all these DRMs. If you're working for a specific program, you don't need all this information. You look at that program and you say, what are our missions going to be on the space shuttle or on the Dragon or, on Starbase or whatever it is that's going up next, right? You focus that in on trying to minimize the information you give. But because the HSRB was looking forward, they did more and showed more. All right. So if nobody has ever done this for you, which I doubt they have, then I'm going to do it now. We're going to run through what these risks are in a nutshell. Okay. And I'm just going to give you a little bit of information that I'm going to tell you about them. Okay. So one of them is bone fracture. And this is one that has historically been read because people are afraid. From the in-mission side, when we did analysis on the loads that were going to be experienced at Moon and Mars, coupled with the bone loss, we figured, you know what, this is actually not very likely to cause a fracture. The types of loads we would experience if people were falling or having accidents or things like that. So it's kind of wishy-washy as to whether that's a real one for in-mission. But the long-term health one, what we still don't know is if those structural changes that happen in the trabecula of the bone are going to have significant impacts later in life. And the last time that I saw any information on it, it did look like the astronauts were having a statistical basis slightly higher fracture rates than they would be expected for a cohort that's similar to them in the general population. Urinary retention is a risk still. In mission, we've had some cases where crew members were swapped out because of urinary retention problems. We give people catheterization. There's a worry that it can lead to more infections, certainly in Apollo 13. When they kept the condom cath on too long, that was sort of prescribed as the reason why he got that infection. We do see more infections in flight and in men than we see on the ground. Is it real? The data is very small n, we're not sure. Aerobic capacity and muscle strength are two risks that I'm mashing together, right? One of the things that we do know is that your pre-flight fitness is the biggest determinant of how much muscle you will lose. And we also know that exercise capability in flight is critical. What we don't know is if you go to Mars and you take away some of the ones that we've got on the ISS, what the effect of that is going to be. And we also really still don't know how partial gravity is affecting our aerobic and muscle fitness levels. So that is stuff we will learn in the future. So it sits at a yellow. Non-ionizing irradiation is a risk. And this is also one like urinary retention that, by the way, the HRP doesn't fund research in these areas, so you won't see them on the research roadmap. But be aware that NASA continues to keep an eye on them. The big concern on that one is sunlight, which is why the protective coatings. And there's some people who are worried about lasers from Earth that, can get through the windows of the space station. Let's just say we've provided the astronauts with eye gear and they don't really wear it. Electrical shock, this is one that we continue to monitor, but there's pretty strong engineering standards in place for minimizing that. Realize that when people are out on EVAs, that there is engineering that is done to keep the suit from charging and causing discharges outside as well. Hearing loss, which I tend to call acoustics, because it's not just about hearing loss. You can have perfectly good hearing, and if there's a whole bunch of noise going on in the station around you that you can't communicate with the people around you, it's not that you lost your hearing, right? It's that you couldn't hear because the noise wasn't mitigated. So it's really an acoustics risk. We do have pretty good standards in place. Throughout ISS, we've never seen ongoing hearing loss in astronauts after they've gotten back beyond R plus 30 days. The Russians actually have seen some, but I can't say much more than that because I don't know. We've gotten a little bit of look at their data. So acoustic engineering is a big concern, especially in human systems integration, to try to keep that risk low. If you take it out, then you have what happened to the space station back in 2003 when the LA Times had a front page article about how the commander was saying we couldn't hear himself think up there. And then NASA had to go back up and replace all the pumps and fans and stuff with quieter pumps and fans. That was a lot of money. Toxic exposure, this is pretty well understood. We have permissible exposure limits available. They get updated on a regular basis. What they really haven't done a great thing with is clinical practice guidelines on what if it does happen side of thing. Celestial dust, this is moon dust, Mars dust. Moon dust in 2014, the LADTAG group did a lot of analysis of it. It looks pretty benign from the animal studies that were done, but obviously it can be irritating to the eyes, the skin. Open question as to whether you can get allergic to it or not. One of the flight surgeons started sneezing after his third time playing with it, and so everybody says that it's an allergen, but we don't really know. And then Mars has some perchlorates and some other things in it that we'd have to worry about, but these can probably be engineered out if we do our engineering smart. Microorganisms. We've been swabbing the surfaces of the ISS since we put it up there. This really, as to whether this is a problem from the human side of things, kind of is in tandem depending on what happens to our immune systems. It's something that we think we've got a handle on, but we'll see. Sleep, we've done a lot of research on sleep, right? Basic human need. A lot of things depend on this. What I will say is that private crew quarters are not a given in any vehicle. It is a constant fight to get them included. Environmental control, including noise, again, that acoustics thing messes up sleep, right? Lots of astronauts have used medications for this. This is a big area where engineers and designs can skimp on trying to manage the sleep issues, and that can cause a downstream chain of problems, okay? Decompression sickness in the context of ISS and future missions really depends on EVAs. That seems to be the place where we go between different pressures. 14.7 psi on the station to 4.6 psi, I think, or 4.3 psi in the EMU. We are in the future looking at exploration atmospheres, which would drop that to 10.4 and 8.2 potentially. There's a lot of research going on in these areas to try to figure out, hey, how do we get away from the 2.5 hours of pre-breathe that we have to do before going out the door on the ISS and not raise their risk of decompression sickness? Similarly, hypobaric hypoxia, right? If we use exploration atmospheres, it's going to make these crews mildly hypoxic, potentially for months at a time. Probably a small effect, but we don't really have great data on it. And this is part of why, we talk about some of these things. AVA injury, how you design the suits has had a major impact both in training and in missions for how crews have been hurt. A lot of astronauts have needed shoulder surgeries because of the hard upper torso design of the EVA suit. New suits are being tested. We're going to find out how well they do, right? This is an area where logging and monitoring injuries operationally can help us figure out design solutions to keep small problems from becoming big ones. There's another class of things. The next ones are, hey, these are things we sort of know well, but we can't do as much about. Kidney stone formation. This has been listed as a red risk for a long time, ever since one of the cosmonauts maybe had a kidney stone and passed it. We've never had a proven kidney stone in flight. And yet it's a red risk, right? Why? Because we've been looking at the urine, and the urine looks like the urine of kidney stone formers. And in addition to that, we've had astronauts come back and get kidney stones after flight. Usually not immediately. Some of them are like 2-3 years after flight. So it's an area of trying to figure it out, right? But because it could lead to incapacitation and potentially to sepsis, it's something we've really tried to work on. And there's early detection. There is potentially pushing using ultrasound, other things like that might bring that consequence side down. Cardiovascular. This used to be several different risks, including arrhythmia, orthostatic intolerance, and radiation damage that were all mashed together because they were about the heart. So arrhythmia was its own risk. We've had 9 astronauts who have had atrial fibrillation, but 0 that have occurred in flight. There is this question of whether somebody had like a run of VTAC in flight. There's some discussion on that. A lot of people think it's settled, but other people that I've talked to have said, yeah, they think it was a electrical artifact, right? And so we struggle with not just the medical side of this, but also the deconditioning side of this, right? Over time, if we don't get the exercise stuff right, what do we do there? And then, orthostatic intolerance is what happens when you go back to the surface and you're in a G domain and all the fluids go down. We do salt loading and fluid loading now, but we also have a lot of people there to pick them up. So what happens at Mars when they're not there? There's still an open question on radiation damage to the heart and the vascular system. How big is it and how big of a problem is it going to be? Not really sure. All right. The dynamic loads risk is about what happens in terms of injuries when you expose people to the loads of launch and landing. And not just launch and landing through the atmosphere, but also think about standing up in the lunar vehicle coming down to the surface. How heavy is your suit? Not in terms of weight, but in terms of momentum that can be generated. Can somebody twist a knee in these things with these types of accelerations, right? So in Standard 3001 Volume 2, you have acceleration limits and bands in there that you can go look at, that we can talk about in other lectures, right? I will tell you that our ability to predict injuries has been crap. We've used the Brinkley model, we've used ATDs and Thor, and we had a lot of injuries in Soyuz that were not predicted by the models. And so there's been a lot of active work in trying to make our prediction capabilities better. Cancer from radiation. This is carcinogenesis, right? This is the one that everybody thinks is the biggest deal out there. But the way that it has been created and presented, the way that REID, radiation exposure induced death, as a parameter has been presented, has been something that deserves its entire own lecture to walk you through so that you understand. I don't think it's as bad as it's been made out, and there's certainly a question of whether or not the assumption of linear no threshold applies in spaceflight to these low levels, constant exposures we see from GCR, but there's a lot of people doing research on that. And it's a big one that we worry about for post-flight. These are the wild cards. These are the ones that I think that can come and jump up and get us later, right? CO2. You won't see this listed on HRP's website because they don't do research into it. But we have worked for years arguing about how low we can get the CO2 levels. We have standards that we created that couldn't be met by the systems that were available. So then we're like, go make better systems. And they're like, give us some more money. And everybody complains they don't have money, right? So the ecosystem struggles to meet the standards that we think of. The only thing that we were able to use as hard evidence for the CO2 system in terms of chronic levels of exposure was headaches that the crews got, We did track those well enough. And then there's these acute exposures that can occur in suits if systems fail. So there's still work that needs to be done on CO2 to make sure that it's not going to become a problem when you have very long duration space flight and you're not sending spares up from the ground, right? The immune system, there's a lot to talk about here. We know that there's a lot of changes happening. So far, the impacts have been small and manageable, but over a 2 to 3 year Mars mission, how big are they going to get, right? Are they going to get big enough to really make the crew more likely to have more or worse infections is really a big open question. And so that dovetails with microbiology and a few of the other risks. Sensory motor or vestibular things, right? This really is sort of a punctuated risk, right? Where do you need to not have vertigo? Well, definitely not when you're trying to dock, when you're trying to land something, right? When you're doing some critical tasks. How big of a deal is it? Is it in between things? Is it only going to happen when we go in and out of gravity wells? We're not sure yet. So there is research that goes on there. Obviously, for commercial space flight, which is different from going to Mars, right? Commercial space flight, your space adaptation motion sickness has the potential to make your paying customers not enjoy it as much. So something else that the business side has to keep in mind. SANS. This space adaptation neuroocular syndrome, right? We have struggled a long time to understand this. And there is one big unknown that is sitting out there. Is it ICP elevation related? In the beginning, we assumed it was. And later we started seeing conflicting data that said maybe it isn't. Maybe it's just vascular congestion and hydrostatic pressure in the blood vessels. We don't know yet. We've been trying to do this for a while. And I can tell you stories about how experiments got derailed. There's one other big unknown that we sort of looked at, which is retinal nerve fiber layer atrophy, which, if it were to happen, could lead to severe vision loss. And so these are still some things that we're struggling with. And we don't know how bad or how big of a deal it's going to be because we're not sure if some of these theoretical things will happen. As it stands for the moment, the only thing we've needed to do to fix SANS, at least operationally, has been to give them eyeglasses. But we don't know if it's going to be a lot worse than that. Venous thromboembolism, we started seeing clots in space in 2018. We found it incidentally on a research study. There's still folks who think maybe it wasn't a clot, maybe it was. The last review of all this stuff suggested there's actually 4 events that have happened in astronauts now since that time frame that are concerning for clots in space. How much of an impact is this going to have going forward? Don't know yet. In terms of the risk board, this was combined with the cardiovascular risk. Pharmaceuticals. There's 2 parts of this risk, right? One of them is, are they going to have enough of the active pharmaceutical ingredient to be functional when you need them? And the other part is your body changing in ways to make them less effective, right? So the storage problem, and will they still work? And pharmacokinetics, pharmacodynamics, is our physiology changing? There's a lot still we don't know here. It probably won't affect us until Mars. Otherwise, we're probably okay. And then these are the biggest ones, right? This is the last of the set. I did combine some together, so it doesn't say 29, but this is the last of the set that, to me, are the biggest problems that we have. Food and nutrition, we still don't have something that can provide a safe, nutritious, and acceptable food system for a Mars mission. In-flight medical, because we've got PRA data that shows this is going to be a big problem. And how do we manage it when we're away from real-time communications, these other things, right? Cognitive and behavioral conditions. This is a really potentially big one. We're relying on cognitive function for those humans to not make all those errors all those engineers were worried about, because they clearly designed in all these error spots. And then how is a team going to function, right? Over that long, being stuck in a Winnebago-sized thing with 3 or 4 of your best friends that you can't get away from. And all of this, to me, is really about the underside of the whole design process, which is the human systems integration architecture. And this risk has been now renamed Earth-independent human system operations, right? How do we do this being independent of Earth? Because we haven't done it that way before. So in that feedback loop, right, all of those things are these risks, and they're setting standards to these things. And we take these lessons and we try to learn how to prevent them. And we do that through creating all these standards. NASA 3001, 7120 for systems engineering, 8705 for human rating. There's all these things that you can go find and look at. And we also create program requirements and flight rules and chits and all these things. And those are designed to prevent things from happening, right? But what happens if prevention fails? Right? Prevention is decreasing the likelihood of something. Treatment or intervention is decreasing the consequence of that thing if it happens. There are 5 ways to effectively manage risk that we have to consider. Understanding it, which is risk characterization, hazard control, which is preventing it, consequence reduction, which is treatment, adjusting system resilience, which is improving margin for the system to be able to respond to perturbations, and then accepting risk, right? And we have modeled our entire risk process on prevention, but we never reach our ideals, right? Prevention is the ideal. We never reach that in real life. So we have to look at the flip side of the coin. So if cognitive error is such a big deal in those 2-week space shuttle missions, how big is it going to be in those exploration missions, right? We talked about that earlier. Let's come back to that question of cognitive function. We know that selecting out crew from the astronaut process, right? That risk reduction benefit starts to diminish sometime between 40 and 180 days. That's our best estimate of that coming from our PRA analyses that are evidence-based. Is it perfect? No, it's the best evidence that we've got right now. If somebody says they don't believe it, ask them what their other evidence is. What you can see here is that this difference between highly functioning or limited risk and piss poor risk is really about how you design and build the system to meet the crew where they are, right? So we have these spaceflight hazards. They lead to certain risks for an individual, which is how we mostly think about these risks when we're not thinking deeply. It's really about individual health. Are they going to be okay? But that health is really for them to be ready to do a job, and they're part of a crew. So in theory, even if one person can't do a job, there's a chance somebody else can, and the job might still get done. But if the team isn't functioning well, maybe that doesn't happen. But even if you have everybody as healthy as they can possibly be, if the system wasn't designed to support them, if you didn't bring enough spares to fix the broken part, then that thing isn't going to be done regardless of how healthy and ready those individuals are. So you cannot deal with this independently of the overall system and habitat, right? The human reliability analysis that the engineers did focused on the reliability of a single crew member with a specific task. We are now in a domain where we have to look across the systems. We have to bring a systems approach, moving beyond human reliability analysis. So this is the DAG for behavioral health and cognitive risk function, but I'm not going to go through the whole thing. I'm just going to point out a couple of things. That individual readiness is heavily dependent on cognitive function. And you see all these little arrows going into cognitive function? That's a lot of things that can affect it and make it go wrong, including stuff from a whole bunch of those risks that we just talked about. Maybe you didn't have the medical stuff, the pharmaceuticals to deal with things. Maybe they had problems in some of these other areas, right? Maybe some of those things stacked up, like sleep and medical problems or poor nutrition. People are not going to be cognitively functioning well enough to have that individual readiness. So why does it matter? Because when we deal with problems with the vehicles on ISS with real-time support, we are 100% dependent on all of these experts working on the ground, working that first hour of a critical situation. 22 unique console disciplines, 50 plus operators on console, 500 years of combined on-console experience, all of the education and training they've had, right? How are you going to stuff that into the 4 people that are on board that ship? Those humans, this is that human reliability analysis, right? All these things are making them deconditioned and potentially affecting their cognitive function. But we need their cognitive function high so they can do the things that we send them to do, right? Anomaly response is a big one. Complex procedure execution, fixing things, knowledge integration, causal diagnostics, all these things. So this is why I say that cognitive function behavioral health is such a big risk, because everything going on in the mission is working to break that down and make you less fit to do those jobs cognitively. And remember, right? This is from early in the lecture. Aircraft malfunctions were a threat in 20% of normal flights, right? 40% of those failure modes in a well mature industry were unanticipated by the designers. So what happens when we go over to the first flight to Mars or our first flights to the moon, right? It means we're really relying on those astronauts to fix things that break. So when prevention fails, we have to move on to treatment, and we need to design some things into the vehicle. And that means a crew health and performance system that is integrated into the vehicle, that has things like environmental monitoring, crew monitoring, all those things to understand where they're at, right? It needs to be able to speak with the group back on Earth, because even if you don't have real-time communications, you still want to be able to use it as a store and forward consult type service, because they're going to be able to help solve problems that aren't in, things that have to be resolved immediately. And you want to be able to do that in a seamless way. So that system has to be able to do all these things, right? Protect from environmental hazards, keep them healthy, prevent, diagnose, treat, and manage their long-term care in mission, support them to accomplish mission tasks, right? That is the crew health and performance system. And it has to fit into that larger architecture of the habitat. All those things have to go there, respecting that the crew can be a physician, the crew can be a patient, that there are ties into all these different subsystems of the vehicle and back to the ground system, at least to MedOps, but probably to more, right? And there are ways that we plan for this in rigorous ways. You can't just say, well, we don't know what's going to happen, so we're not going to do it. We plan out all the things that need to be a part of this system to do the planned activities, right? Mental health care, preventive care, exercise, monitoring, right? Those are all going to be defining capabilities that we need in that system. And then you look at the unplanned side. We hope it doesn't happen, but there's a chance it will. This is where the expected medical conditions come in, right? The medical conditions list that we worry about. And we think about, okay, what's the probability of occurrence? What's the frequency of occurrence? How bad can they be? Is it worth treating somebody, right? And what are our resource constraints? And when we roll those things up, we have to decide on an accepted medical condition list. This is the stuff that we are saying, yea, verily, we are going to provide the resources and the training to go try to deal with these things. And the other things we're not. And those things will fall to a common pathway, which is palliative care. Okay? Those things, once you do that, you can define the sets of capabilities and feed them in as functional and system requirements to the systems engineering and integration teams. And you can read this article down here on how we've done that process. So that system is not going to be like an ICU, right? It's going to be something that's a little bit more like a tablet, a lot of it information-based. How do we decide what to do? How do we monitor the crew? How do we make diagnostic things? It's not huge. It's mass and volume limited. And it really depends on how we integrate that crew health and performance system with the larger vehicle throughout the systems engineering life cycle, right? And that process has a name. It's called human systems integration. It tries to make sure that the human, the software and hardware components of the system cooperate, coordinate, and communicate effectively. It places the human concerns on par with other aspects of systems design, right? And it's got a standardized process and uses these technical disciplines to participate in all of the formulation and system development, right? Every step of the way. Why? Because that human system integration mitigates the risk of system failure, including three of the most common causes, right? Underuse due to poor design, human error, and high operations and maintenance costs. If we do this rigorously and human-centered, right, then we can actually capture all of our information, feed it in, and continue to decrease risks. And the reason why this matters, not just because it makes the crew safer, but because it saves a ton of money. Life cycle costs are locked in early. You get through phase A here, and you've already locked in potentially 60% of your costs. You've already committed them. And if you locked in a design error that you need to go fix later, it costs a huge amount more to fix it later in the process. This is why HSI matters in systems design. So we started with talking about human error analysis, human reliability analysis as the way that the engineers viewed risk. We went through some of the history of how we got built up new ways to think about risk, right? And those are the ones that have been implemented at NASA so far. And that's where we come into merging the importance of risk management and human systems integration into the systems engineering process as an appropriate way to actually manage and mitigate risk. Now, what we're going to talk about when we get to the next lecture is how to quantify risk. Because I've shown you some graphs, but we haven't talked about the modeling that goes into it, the data, what that actually looks like. And also, we'll get to levels of evidence and causal diagramming. So the next one really is about how we can make sure that you as a physician are not scared of math or computer science, and can understand what people are saying when they use PRA analysis, what it should be used for, what it shouldn't be used for, and how you fold that back into risk decisions. All right. I'm going to stop there. Brian, what was confusing?
No, I thought it was really, really good lecture. I really like how you really clarified first of all, the definition of like standards and how relevant it is here. I think it's kind of like standards, even though they're designed to like be, you have to clarify and be anti-nebulous. Like, I feel like they're kind of thrown around in this like nebulous way. It's like, what does a standard really mean? Mm-hmm. But in this context, it like really makes sense. So I hadn't really thought about it that way, which was great.
This is one of those things that it's really important to kind of get a sense of, right? Because people who are not sort of familiar with it will call out standards and like they're problems that have already been solved, right? And, they'll look at OSHA. And I told you, there was a paper that was suppressed that I wrote inside because I actually said that the way we think about standards and the way that NASA standards are evolving precludes them from being effective for Mars missions. So therefore, we should actually just make all astronauts research candidates rather than people who are subject to standards. And of course, they didn't like that. But what you get at OSHA, for example, right? When we make a standard in terrestrial terms, we're taking a ton of information and saying, this is what keeps people from dying, right? And we're basing it on a huge amount of data. When we do it in spaceflight, we don't have that kind of data. So the standards are more of a reflection of this is our best guess so far. And like I said, it's a mixed bag. So think about the OSHA standard for radiation exposure. OSHA actually makes an assumption that has unfortunately sort of become common knowledge, right? Their assumption is that they're dealing in a linear no threshold domain for radiation exposure. What does that mean? It means they're saying that no radiation exposure is okay, right? All of it is going to do damage. But we have this curve, and we know that we go down to the lowest end of the curve, you're still doing damage that is unacceptable. And that's not consistent with homeostasis or reality in the biological world. We've evolved in environments that have some level of radiation. So we have repair mechanisms. So when you say that the linear no threshold theory, right, maybe doesn't hold, what you're saying is there may be a threshold below which our body is keeping up with the damage that's done, right? And the flux, the dose rate from GCR over time may fall below that threshold, right? And so the answer is we don't know. But if you make the assumption, what you're doing is you're saying we don't need to go do any research at these low radiation levels because we're just going to assume that it's all bad. NASA spent $40 million a year for since 2010 or 2011 on radiation modeling. Didn't drive down the risk at all. It just made our modeling better. But in a different lecture later in the year,
I'm a big fan of the radiation hormesis theory, especially when trying to convince patients that the CT scan's not so bad.
Yeah. So, Anna, I see you there.
Hey, good morning. This was an awesome lecture. especially just highlighting how common, unfortunately, it is that engineers are like, we can just kind of push the human element down the road a little bit. Worrisome for Mars missions. But I like your proposition about the standards for Mars missions and essentially just kind of using everyone as not a guinea pig, but you know what I mean.
Yeah, they will be ultimately, whether we call them that or not. They will be
lab rat in the night turf for lab rat.
So okay, you got any questions before I get off?
No intelligent ones. Nope. But this was awesome. Thank you for making it available.
Yeah, we're gonna have another one. What, Wednesday?
Yeah, Wednesday, same time.
Sounds right. Okay, cool. Well, then I'll see you then, Brian. Whoever else shows up.